So as in the title, I'll talk about what's this classification of sense-fan threefolds in positive characteristic. So I work over a direct closed field of positive characteristic. Main result is this: the first threefolds in positive characteristic are classified as in characteristic 0. So I mean, the classification table is almost all the same as in characteristic 0. And here, in this talk, I always assume that first threefolds are smooth. So in this talk, I do not consider the singular fan threefolds. So I just say fan threefold, then it means that it is smooth projectibility and the minus kx is ample. So before giving the whole picture of classification, as I first want to explain two invariants of for fan threefolds. And the first one is not only for fan threefold, but it's just a Picard number, which is equal to the rank of the Picard group. So this is not trivial in positive characteristic, but this is proved by Kawakami and Shepard-Baron. And more explicitly, more strongly, we have the isomorphism. The Picard group is isomorphic to free abelian group whose rank is equal to the Picard number. So I mean, linear equivalence is equivalent to numerical equivalence. This is not my result. This is proved by Kawakami and Shepard-Baron. Next, I will try to explain the second invariant. It is Fano index. In this, I will denote it by Rx. So this is called the Fano index or just index of x. It is the largest positive integer which divides minus kx. So in other words, minus kx is divisible by Rx. So we can find ample Cartesian divisor such that minus kx is linearly equivalent to Rx times h. And if we pick larger positive integer, then we cannot find such expression. I mean, if s is larger than Rx, then that does not exist. Sorry, here h exists, but for s, such h does not exist. And as in characteristic 0, we know that Rx is from 1 to 4. This follows from the Kohn theorem by Mori. So by using these two invariants, first I would like to give whole picture of the classification. So let us recall what happens in characteristic 0. In characteristic 0, so in the roughly speaking, there are three cases. The first one is proved by Iskovsky and Shokrov, which treats the indexes at least 2. The second case is Picard number and index are both equal to 1. This case is also done by Iskovsky and Shokrov. The remaining case, I mean, Picard number is at least equal to 2. In this case, has been settled by Mori and Mukai, so which means the extreme array and Kohn theorem. In positive characteristic, basically we follow the same strategy as in characteristic 0. The first case, I mean, the Fano index is at least 2. This case has been settled already by earlier work by Migesi. So basically, in this talk, I'll focus on the second case. So I'll explain this case in details. As for the third case, this is identical to the case of characteristic zero. So as I said, I will give a detail for the second part, but before that, I want to explain, I want to give an overview for the first and second case. Sorry, first and third case. So for these two parts, I do not give the details. Okay, on the first part, as I said, this is the result by Migesi. So this is a classification for the case when the index is at least 2. And so I skip the case when the number is at least 2. So I assume index is at least 2 and picarial number is is equal to 1. The classification table is written here. So as I mentioned, the index is from 1 to 4. If it is equal to 4, then it is P3. If it is rank is equal to 3, then it is smooth quadratic hypersurface inside P4. Then now I assuming this condition and Rx is from 1 to 4. So remaining case is this one, R is equal to 2 and rho is equal to 1. Then by definition of the index, we can find ample quantity divisor, which is such that minus k is equal to 2 times h. Then there are 5 cases as follows. If h cubed is equal to 1, then it is weighted hypersurface inside this weighted projective space of the U6. And similarly, h cubed is equal to 2, then like this. Then h cubed is equal to 3, this is cubic hypersurface. Then h cubed is equal to 4, then this is complete intersection of two quadratics. And finally, h cubed is equal to 5, then this is linear section of Grassmannian to 5 inside precarium thing. Okay, I do not give the detail on this one, just I want to show this is actually classified. So I want to go to the next case. I mean, I do not give the detail of the classification, but I want to explain the idea of the classification for this part. So in this part, the key notion is this imprimitivity or primitivity. So we say that Fano threefold is imprimitive if it is obtained as a blow-up along a smooth curve, and it's and y is also Fano threefold. So in a sense, in primitive, if given primitive Fano threefold, we can make it smaller. We can find smaller Fano threefold. So basically, this is the strategy by Mori and Mukai. So what we will do is the final goal is to classify all Fano threefolds but to this end, it is enough to classify primitive Fano threefold. So this is the main idea of Morimoka's strategy. So what in the next page, I would like to explain what does this mean. So if we have Fano threefold, which is not primitive, which is imprimitive, then it is obtained as a curve blow-up of Fano threefold. If we, again, this x1 is imprimitive, we can repeat this procedure. I mean, x1 is obtained by curve blow-up from another Fano threefold. Then we repeat it, then we will achieve primitive Fano threefold. Then what we need to do is to give a classification of primitive Fano threefolds. Then after that, in order to classify in primitive Fano threefolds, it is enough to compute this blow-up procedure. And this sequence terminates because the number is a positive integer and it drops strictly. So this is positive integer, and by one blow up, it drops by one. So this sequence terminates. Okay, so this is I do not give any details, but this is I just wanted to show you what is the main idea of classification for the case when Picard number is at least 2. So now I want to focus on the main part of this talk. This is the remaining case, and this is the main part of this talk. So let X be a smooth Fano threefold satisfied in this property. So Picard number is equal to 1 and the index is equal to 1. Then the first step of the classification is to consider the anti-canonical map and study the property of this anti-canonical map. Then under this condition, we can prove the following result. First, this minus kx is base point free. So we get a morphism from x to Pn. So we take morphism to its image and denote it by psi. Then we can show that this psi is a finite surjective morphism whose degree is equal to 1 or 2. Then, so we need to consider these two cases separately. For the case when this psi is a double cover, it is we can classify it very explicitly. For the other case, I mean, degree psi is equal to 1. This means that the psi is biational. In this case, this is actually isomorphism. In other words, this minus kx is very ample. So let me show you the overview of the PIC proofs. First, these two parts are easy up to no result. So, for example, for the second part,
So you mean the specification of degree 2 case is easy, like even in the case when the characteristic is 2?
So yes, I mean, so for example, I just say that psi is a double cover of P3, which can be inseparable, but I do not exclude the possibility of inseparable case. So it can be inseparable or separable. I don't know.
But so this inseparability doesn't make any big differences, does it? I mean, it's hard to imagine that this inseparability doesn't lead to any difficulties.
Sorry. In this case, sorry, I remember. So in the classification table, so there are many double covers, but if I remember correctly, this case, as Megesi proved that this is actually separable, but I'm not so sure. Anyway, so in my classification table, I allow that this is just a double cover, but it can be inseparable. So I do not check whether inseparable cover actually happen or not.
But anyway, do you so in this particular case, when it is a double cover, does one have an explicit classification of these varieties? I understand that one can describe them as a double cover of the varieties of some small list, right? Like varieties of minimal degree or whatever. But for instance, characteristic 0, one can improve this description by just by adding details to the description. So do you make this step as well?
So you mean, so for example, in characteristic 0, so double cover is obtained by suitable section of line bundle.
Well, for instance, we know that there are only a few cases in characteristic 0. There are only a few cases in this subclass, and they are like sextic double solid and something and something.
So at least in this case, so I think if I remember correctly, so there are only this one and this one.
Exactly. Yeah. Right.
And maybe yeah. At least the base of double cover is the same as in characteristic 0.
Yeah. The basis is the same as characteristic 0, and
maybe V1. This is no. Sorry. Okay. Yeah. That's two cases. Yes.
Okay, so the result is that the base is either P3 or Q, and then you don't give further details.
So yeah, I saw that this is a goal of the classification. So I did not give any more details.
And for instance, maybe it's the question about the subcase. Suppose that you have a double cover, and suppose that characteristic is 2, but suppose that the double cover is separable. And so you have a double cover OP3, and what's going to be the branch divisor?
So
it's not going to be a sextic anymore, right? Because sextic would be a fun variety at all.
So usually I think it depends on the definition of branch divisor. So I mean, in characteristic 2, I think it will be half of usual one. So in characteristic 0, I think this branch divisor, this is degree 6, right?
Yeah, right.
But in positive characteristic, this is branches usually becomes a half of usual one because I think in characteristic 0, double cover is given by like this. But in this is over C, but in characteristic 2, double cover is given by like this. So we cannot make complete square, so this term cannot be erased. And this S1 gives the branched locus, because if this is vanished, if this term is erased, then it becomes inseparable. So usually branch divisor, branch locus is usually becomes half of the usual degree. So in this case, degrees, branch divisor becomes degree 6. But in any characteristic, we have this description. This always, this is characteristic free description. So L is same, but this error is same. But the branch becomes different from characteristic 0, or only in characteristic 2.
And once again, so we don't know if it can be separable or not, and in particular, we don't have inseparable examples. Is this true?
So in this case, if I remember correctly, Megeshi's paper includes that inseparable cover does not happen for this case. Hyperelliptic case, I think Megeshi settled the hyperelliptic case. So I mean, these two cases are settled. So separability is okay, I think, yeah.
Thank you.
If I remember correctly, yeah. Okay, so I think I was explaining these two easy cases. Then for example, so Y is defined as the image, so selectivity is clear, and minus kx is a pullback of ample on Y. Then since minus kx is ample, then it should be finite. So these two parts are very, very easy, and by using the degree of the variety or using delta G naught by Fujita, we can show that this degree is equal to 1 or 2. Then following the argument in characteristic 0, we can show that we can classify the case of characteristic 2. As for the part 4, in this case, in characteristic 0, we take general hyperplane section twice. Then the problem relates to the net as theorem for smooth curves. In positive characteristic, we cannot assure the smoothness, but still, Gorenstein is okay by taking the general hyperplane section. Then we can apply net as theorem for Gorenstein case, which is known. So here I want to say, I mean, net as theorem means that if case is ample and its complete linear system is birational, then it is very ample and projectively normal. Then project normality lifts from curve to threefolds by surjectivity of CW surjectivity of H0. So this is the proof of part 4, which is exactly the same as in characteristic 0. Then now I'd like to focus on the remaining case, part 1, which is the base point freeness of minus kx. This part is actually very long. So I want to first give us, I want to give a sketch of this part, and then I would like to focus on which part is actually quite different from characteristic 0. So let us start by recalling the proof of characteristic 0. As I mentioned, this part is under suitable assumption, minus kx is base point free. This is the goal. The proof consists of 3 steps. First, we take the decomposition into the modal part and fixed part. Then we can show that f is equal to 0. Then, and if we take a general member of minus kx, then it is actually smooth. Then by using adjunction formula, we can show that it is K3. So smooth K3 surface. Then we are interested in this vector space. Then since we know that general hyperplane section is K3, so we want to use information from K3. Then we got the restriction map. Then this is surjective by the Kodaira vanishing theorem. So the conclusion is as follows. We are interested in the base locus of minus kx. The goal is to show that this is empty. This surjectivity shows that this base locus is the same as the base locus after taking the restriction. Here, this equality holds as scheme. Then by using the result on K3, we see that. And this is isomorphic to P1. So in a suitable setting, we since S is K3, this base locus is isomorphic to P1. Then the final step is to take the blow-up along this base scheme, which is isomorphic to P1. Since we take the blow-up along this base scheme, we get induced morphism here. Then by computing some fiber of this morphism or some intersection number, then we get contradiction. So this is an overview of the proof in characteristic theorem. So basically, we follow the same strategy also in characteristic P. So this is basically based on Schwarz-Baron's idea. In first part, we take general member. So as you can imagine, here we use Bernoulli theorem and Bernoulli theorem for base point free linear system, which is not true in positive characteristic. In order to overcome this difficulty, we will use generic member, which is as a replacement of general member. Then we have a Bernoulli theorem for generic member. The illustrating result is as follows. So given a smooth projective variety, and we have a base point free linear system, then after taking suitable field extension, then we can find the regular member. After taking base change, we can find regular member. For the original linear system, there are no smooth member. But after taking suitable base change, which is actually purely transcendental extension of finite degree, then we can find such member. So Bernoulli holds it after taking base change. Then, in a sense, the remaining steps are similar. For example, we need to work over this mu-based field, kappa, which is no longer a direct closed field and no longer perfect field. But still, we can show that we can establish similar results for K3 surface, which we call K3-like surface. So here, I mean, this is K3-like surface because this is very similar to K3. And this terminology is introduced by Schwarz-Baron. This is regular projective surface. whose canonical divisor is trivial, and H1 of O is vanishing. So if regular is replaced by smooth, then this is the usual case with surface. But regularity is weaker than smoothness. So this is wider notion than usual case with surface. Anyway, so we can show that this isomorphism, then this is just a formal computation, but this is, so this is the same as in character zero. We can we know the vanishing of H1 XOX, then we get equality. Then and just comparing the base change. Then after taking the base locus, taking base locus is commuting with base change of the base field.
And sorry, and do you really need projectivity in the theorem?
So projectivity of what? Sorry.
In this Kumino-Greco monoresis theorem and Tanaka theorem?
Oh, no. This does not need. I
Because I think
we
actually
only.
I'm going to apply it on something on some like open because you multiplied it
Well,
just outside base points on the projective variety.
yeah, exactly. So we here. Oh, sorry here. So here we can omit this one. Yes, exactly. Yes. So yeah, yes. Okay, what I wanted to say is yes. So now what we are interested in is this base scheme. The goal is to show that this is empty. What we know that this after taking the base change, this becomes P1. Then this scheme must be P1 before taking the base change. So this is exactly the same result as in characteristic zero, but we need to factor through the imperfect field kappa. Then the third part is actually the same as in characteristic zero, so I didn't give any more details on this part. So in a sense, in this proof, the newest part is taking the generic member here. So I would like to explain what is this. I want to give more details. So this generic member is used also for the other part. For example, smoothness of threefold flops is proved by using this generic member. And also we need this notion to assure that X is an intersection close X under suitable assumption. So we take a base point free linear system on a variety X, then it corresponds to a morphism to projective space. And recall that giving a member of phi is equivalent to take a hyperplane on the target. So they are connected by taking the inverse image of this morphism. So what we will do is make everything to be generic. I mean, this generic member is defined as the inverse image of the generic hyperplanes on this projective space. So I will give a definition of generic hyperplane, but before that, this phi kappa is just a base change of the original morphism. So now I want to focus on Pn and its generic hyperplane. So recall that hyperplane is given by the following diagram. Here, we start with this projective space, and we take the dual projective space, which parameterizes all the hyperplane. Then this product space, we have inverse hyperplane. I mean, by taking a close point of this one, then its inverse image is a hyperplane. Then what we will do is to make this to be a generic, which means that instead of taking close point, we take generic point. So generic hyperplane is a generic fiber of this morphism from H unit to this dual projective space. So we consider, so here is the same. So we take projective space here and dual projective space. Then we have in the product space, we have the inverser family. Then we take the generic point. So this is a fraction field of Pn, and it take its spec. Then we take the fiber product for this one. Then now this term here, this becomes kappa. So this is P large and kappa. Then we again take the fiber square, which is nothing but the generic hyperplane section, generic hyperplane, which is the generic fiber of this composite arrow. As I mentioned, this is generic point, so kappa is equal to the function field of this projective space. So this is a purely transcendental extension of the original base field K. So in order to understand more clearly, so I would like to give some remarks. So first, so this square is the same as before. So we have the base field and its and the project space, and I introduce coordinate xi, and we have dual projective space, and it is a isomorphic to project space, and its and coordinate is given by ti. Then this universal hyperplane is defined by this equation, T0 x0 plus delta plus Tn xn. Then using this Ti, or more precisely, we first use non-homogeneous version. So S1 is equal denotes T1 over T0, and Sn is equal to Tn over T0. Then we take generic point, but it factors through any affine of subset. So this x AN is has a coordinate S1 to Sn. Then under this notation, kappa is equal to the function field of Pn, but it is equal to function field to An. It is equal to Ks1 to Sn. And by using this explicit description of inverser family, the generic hyperplane is given by x0 plus s1 times x1 plus sn times xn. Probably it might be specify what is the ambient space. So as a by using approach, this can be written as like this. So which is a hyperplane of projective space whose base field is equal to kappa. This one. As we have defined the generic member, so we can now define we can now define the generic member. So we start with the base bound field linear system, but it's the same as giving morphism to projective space. Yeah, as before, we set kappa to be the function field of dual projective space, which is isomorphic to this pure intertranscendental extension. The generic member of this morphism is defined as follows. So as I said, so usual member is a inverse image of hyperplane, and generic member is the inverse image of generic hyperplane. So we take generic hyperplane inside this projective space. Then just take the inverse image. So this is generic member is Cartesian was on this new variety. Now I'd like to explain why Bertini holds for this generic member. We consider this diagram. So we have first ignore X, just consider projective space. Then from generic member to original projective space, we have another factorization, which is a factorization. So it factors through the universal member because the generic member is the generic fiber of universal member. And the universal member has a morphism to project space. And it is easy to check that this is Pn-1 bundle. And actually it is a project space bundle associated to the tangent bundle on Pn. And this morphism is affine locally a localization. I mean, this is just a generic fiber. So given a ring A, this is the generic fiber is can be written as S inverse A or like that. And by definition, this generic member is obtained from X by taking this fiber square. Then by using this observation, we can show the Bradini theorem for the generic member. So Bradini means that if X has nice singularity, then this generic member has nice singularity. For our application, the most interesting case is probably if X is smooth, then this generic member is regular. This holds because when locally this is a regular ring, then it is well known that its polynomial ring or its localization are regular as well. Then use this diagram. I mean, this is taking polynomial ring, and this is taking S inverse. So both arrow preserve the regularity. So this generic fiber is regular. Oh, okay, so let me show you one example of generic member, which is understandable by generic fiber. So we consider the surjective morphism from smooth projectibility to P1. So this is a fibration over P1. Then we consider so this is a morphism to projective space. So it corresponds to linear system given like this. In this case, the generic member is equal to generic fiber of this fibration. And as I said, this is regular projective variety over this new field kappa. In this case, kappa is equal to the function field of the projective space, which is isomorphic to Ks. So it's the purely transcendental extension of K of degree 1. One of the most typical example in this situation is the province of P1. So I want to further specialize the situation. Then let us compute what is the generic fiber for this case. So this is, of course, finite morphism. So we can compute the generic fiber ring theoretically. I mean, we take A1, which is open P1. Then just it is enough to compute the generic fiber of this province, which can be computed by tensor product. So usually it is considered as endomorphism, but I want to change the variable in order to distinguish them. Then province can be written as this ring of homomorphism, x goes going to y to the p. So we take the generic fiber, which is nothing but a tensor product over this one, and we take the function field of this one, which is nothing but this yeah, nothing but this. Then this ring extension is an integral extension. So this is equal to the function field of this one, so which is equal to ky, which is a field. So in particular, this is regular. So the generic member is this one in this case. I said that this is a typical example. So because this is fiber over any closure point is not reduced. So in particular, not regular in this case. Actually, so similar, we can apply similar computation. So for the generic member, we take the tensor product with a function field. But if we take a fiber over closed point, then the computation in this field is replaced by kx over x minus a. Then this is isomorphic to ky over y to the p minus a. But in positive characteristic, this is not reduced like this. So this is not reduced. So this example shows that even if we cannot use the usual variety theorem, but there's a possibility. So this generic variety is applicable even if we cannot apply the usual variety theorem. Okay, now, okay, I want to go back to Fano threefold, and I want to consider the remaining case. X is Fano threefold such that rho and R are equal to 1 and minus k is very ample. Then the result is as follows. If we define G as usual, I mean minus kx cube is equal to 2G minus 2. It means that if we take hyperplane section twice, then the G is equal to the genus of that curve.
Hiromu, and can I ask, just to summarize the previous part about...
Yes, sure.
So as far as I got it, the main idea of the previous part is that we cannot, we want to study the base locus, and we cannot do it with the usual Bertini theorem, and then we need this new type of Bertini theorem with some transcendental, purely transcendental extension. And but so basically you say that after this extension there exists a divisor in the linear system which is so to say nice, like regular and maybe something else.
Yeah, exactly. So for example, under suitable condition, we can find member which after taking base change, we can find a regular K3 surface of minus kx. Minus kx is linear equivalent to K3-like surface after taking a base change, but I do not know whether we can find actually a member, K3 member before taking a base change.
Okay, but then finally, after all this auxiliary facts are proved, then what do you conclude about the variety? So in this case, you make some conclusion about the initial variety, right?
Yeah.
Before the base change. After all, the aim was to classify the varieties over the field which we start with. And what do you, can you remind me, what do you conclude in this case?
So for example, so for example, one conclusion is here.
Yes, the base locus is P1 because it is P1 after the base change.
Yeah, exactly. So we need to factor through the imperfect field, the prior transcendental extension. We get that it becomes P1. So originally it is P1.
Okay, nothing becomes P1 after a pure transcendental extension except for P1 itself.
Yeah, it is smoothness descent, and also H1 or genus is preserved. H1 XO, H1 COC.
Okay, and then after this we proceed like in characteristic zero to get a classification in this case when we already know that the base locus is P1. Then
yeah. So actually, so
the same as in C, right? Okay.
So I did not classify since 534 whose minus kx is not base point free. So I think it should be not so hard, but I just did not check it.
Okay, so in the final answer, you just have this class when the base locus is P1 and we don't know more details.
Yeah, because this is this is not the goal of the proof. So the final goal is to get a contradiction. So
Okay.
under assuming rho and R is equal to 1, Picard number and index are equal to 1, then I assume that the base locus is not empty, then we can show that this is P1, but finally we get the contradiction. So in a sense, this
Okay, I see.
That's not produce nothing, but under suitable assumption, I can show that the base locus is actually isomorphic to P1.
Thank you.
Yeah.
Also, I have a question, maybe a simpler one. Do you use Shakurov's theorem in characteristic zero here on this step?
Yes. So I think this part is coming from Shokrov's paper, I guess, if I remember correctly.
So this is not avoidable. So anyway, you need this stuff with Shakurov theorem. Okay, I see.
Yeah. Yes, this part is basically Shokrov's idea plus generic member.
The question not about idea. This question about the result. To use this result.
I did not use that by Shokrov.
So your proof can be considered as a new proof of smoothness of anticanonical member, right?
Oh, so I think Shokrov's original paper contains some gap.
Yes. I mean that.
So I just corrected.
In principle, the question is your proof is applicable to characteristic zero case?
I think if I remember correctly, I first give a proof in characteristic zero, which is corrected by which corrects the Shokrov's proof, but that proof does not work under full generality, so I just give a weaker version. So at least I think Shokrov's paper can be fixed by using a suitable vanishing theorem, but I think Reader's note is not enough. So at least I give a proof, but it's I don't know this is new or not. If we apply my proof to character zero.
Okay. Thanks.
Now, I think I was changing the topic. So after finishing generic member, so yes, this one. So I tried to talk about this one. So X is smooth from threefold, and assume that Picard number and index are equal to 1, and mask is very ample. Then we define G as usual. Then the result is G is at most 12, and there does not exist smooth curve on X, such that the blow up along this curve is not Fano. So sorry. So if I mean so take a smooth curve and we take blow up, then it is not Fano. So we cannot find such. Yeah, we can smooth curve satisfying this property. So again, so I would like to start with the character zero proof. We first take blob at a point, then we can find a conic. Conic means a curve whose intersection with mass k is equal to 2. Then we take a blow up along this conic, then we can find a line, and we can show that this at most 12. Then this third part is not needed for this theorem, but by taking a line blow up, we can show that this is not equal to 11. Okay, so now I want to explain what works in positive characteristic and what does not work in positive characteristic. In characteristic P, the first part and second part are okay, except for the existence of line. This part has obstruction. And actually, these two parts are open in positive characteristic. So in characteristic zero, this second part is used. Sorry, the existence of line is used to assure the second part. So I gave a different proof from characteristic zero. So we have 3 parts in characteristic zero, but I use the fourth part, which is the proof of the second part in positive characteristic. Then, roughly speaking, all the parts are very similar. And in a sense, the fourth part is a complicated version of the other cases. So I would like to start with the simpler case. Then I'd like to explain how to modify or what is the difference from the simpler case. So I only give one case under suitable assumption. So we take a point of smooth span threefold and we take a blow up at this point. And let me assume that minus ky is ample. So this is, after taking a blow up, assume that this is still ample. So this is y is still Fano. Then y is a smooth span threefold whose Picard number is equal to 2. So we have exactly 2 extreme array. The one of them corresponds to this blow up. So we have the other extreme array. Then we get another contraction to normal variety W. And Mori classified these classified the type of tag, and Cora extended this classification to positive characteristic. And for example, it is classified C, D, E, and E has 5 subcases. So here, let me treat the case when tau is equal to tau is of type E2, which is as the same as sigma. I mean, W is again smooth projective threefold, and tau is a blow up at a point. So we have a point in W, and its blow up is isomorphic to P2. Then, as I said, for the conic blow up, we get bound of genus. Genus is at most 12. Then from the point blow up, we get a similar bound. It is slightly worse. I mean, we can show that G is at most 13. But anyway, let us explain how to achieve this inequality.
Is it 13 or 12?
So now, okay, so 13 is a goal. In this example, 13 is a goal. But yeah, from point blow-up, we can only get this worst bound. But after that, we can also show the existence of conic. Then by similar method, we can prove the better bound. I mean, G is at most 12. So at least in this example, yeah.
But on this step, you need some things like a smoothness of slopes, right?
Yeah, I mean the smoothness of slope, yes. But yes, but sorry, I do not talk about that. But yeah, it is a new result. But in this talk, I don't talk about it in details. Yes. Okay, so let me explain what is the main idea. So we compute this intersection number. So D is this P2, which is an exceptional divisor of this blow up. And we compute these divisors, these numbers in two ways, which is corresponding to tau and sigma. Oh, sorry, I put copy here. So okay. So first we compute by using tau. Then this is just exceptional divisor of the blow up, and we take intersection number. So these are well known. So I skip the details. This is just a well known result. Then from so we want to know get some information from sigma. Then we first have this equivalence. This is linear equivalent to like this. So if we drop this positivity, then it is easy because x group of x is generated by kx. So after taking blow up, pick y is generated by ky and exceptional divisor. Then by easy observation, we can show that this is actually positive. So alpha and beta are positive integer. Then, as I said, we compute this intersection number, and we use information from sigma. So let us compute this one. Then we apply substitution from this linear equivalence here. Then D becomes this one. Then this is just here is just simple arithmetic, and we have this is again easy because ky cube y is obtained from x by a blow up at a point. Then minus kx cube is 2g minus 2. Then by using, then we can compute k minus ky cube. Similarly, then we can compute explicitly. Okay, this is a okay, now I explaining the computation of this one. Then the other one is also the same computation. So I skip the details, but the result is like this. Then now I give the computation by using sigma. Then combining this, we get this is equal to 4. So this is equal to 4. And this is equal to 2. Sorry, minus 2. And I just write down this equation here. So this is what I wrote in the previous page. Then from here, just high school mathematics or junior high school mathematics. So we just erase G, or maybe 2G minus 10. Here is 2G minus 10 appear twice. Then 2G minus 10 times alpha square is appearing in 1 times alpha. Then 4 beta plus 4 times alpha. Then in the second equation, 2G minus 10 times alpha square is here. So the remaining becomes like this. And looking at this term, this one, then we have common term here. So this goes to here, then the equation becomes like this. Now recall that alpha and beta are positive integer. So this is beta is positive, so right-hand side is at least 0, and left-hand side is at most 0, because alpha and beta are positive integer. Then these are equal to 0. Then beta is equal to 1. So by using the first equation here, we get, and we divide by 2, then we get G minus 5 times alpha is equal to 4. Again, this alpha is positive integer and G is integer. So C minus 5 is equal to 1 or 2 or 4. So G is 6 or 7 or 9. So we get a bound for G. So as I said, from the point block, we get Ross bound like this. From other subcases. But then, anyway, also, this computation works for the conic blow-up. So this is explanation of the point blow-up or conic blow-up computation. And I said that we have 4 cases. Then the first part 4 is the harder than the other case. Let us recall what is the goal. So X is a suitable Fano threefold, and assume that we can find a smooth curve along which we take the blow-up, then y is again Fano. Then we want to get a contradiction. I mean, and there does not exist such a curve grammar. Again, as I said, this proof is similar as before. As in the above example, we compute it, explicitly. But we have more parameters, and the genus of gamma or degree of gamma. So in the former case, we have 3 parameters, G and alpha and beta, and moreover, we have 2 more parameters. So we have 5 parameters, G, H, D, alpha, beta. But as a very was bound, each of these is at most 50, and of course, G is at most 12. But anyway, everything has explicit upper bound. And we have the Fontaine equation as before, involving H and D and G and alpha and beta. So for human beings, it's almost impossible to compute one by one. But for computer, this is very easy to carry out. Then computer tells me that there is only one solution for these 5 parameters. For the for example, for the E1 case, this is actually the hardest part. So then, but the remaining case is only one. Then by suitable computing cohomology, then we can rule out this case. So this is a idea by using computer. But in my preprinter, I also gave a proof without using computer. Well, I want to explain not the full detail, but some of the ideas of this proof. So as I said, the hardest case is when this tau is E1. I mean, B is a smooth curve, and this tau is a blob along this smooth curve B. As before, we have so Y is now assumed to be smooth Fano threefolds. So we have exactly 2 extreme arrays. One is corresponds to sigma, the other is correspond to this tau. Then it is easy to check that they can be written as this. This is the same as before. Then for the E1 case, we have we see that alpha plus 1 is divisible by beta. So alpha plus 1 is equal to beta times gamma, and alpha, beta, gamma are positive integer. And this beta is the index of W. So W is smooth Fano threefolds in this case. Then we have, and there are 3 numbers we can compute. Then we get 3 equations, A, B, C, and we mainly use 3 equations like this. So I do not explain this one, but I just want to mention that the G and D and H and beta and gamma are involved in this equation. So in the former case, alpha is involved, but the alpha was replaced by gamma. So anyway, we have 5 parameters here. So in order to compute by hand, we want the number of computation this. Then first, we make an observation that there are not so many possibilities for pair beta and H cube. because beta is the index. So this is from 1 to 4. Then if beta is equal to 4, then this means that W is isomorphic to P3. So H cubed is equal to 1. Then by similar observation, we see that there are just 17 possibilities. So after we fix other parameters, then we can compute this case by hand. And another observation is this. If H is fixed, then it is not so hard to carry out the computation. So let me show you one concrete example. So let me fix H. And as I said, we can basically fix beta and H cube. So let me just pick beta is equal to 4 and H cube is equal to 1. So I mean, W is isomorphic to P3. Then from the equation C, we get this equation. I do not give the detail, but this equation becomes like this. And in order to get a good bound, what we look at this term. So if gamma is very big, then it is impossible that this becomes integer. So, and we can also use a simple elemental arithmetic. I mean, this number is contained in here, then also contained in here. Then after that, we can get, and this gives strict, strong restriction. I mean, after taking module gamma minus 1, we get this equivalence under this module gamma minus 1. Then gamma is equal to 2 or 12. Then both cases can be excluded. For example, if gamma is equal to 2, then this fraction is integer, but like this, then it is impossible. The other case is similar. So I now show you that if H is bounded, then H is fixed, then the problem is settled. So the remaining problem is how to get the reasonable bound for H. So what we want is a bound for H, and we can actually prove that H is at most 6. For that, we will use the equation A. So we assume this one. Then the equation A is like this. So this is a gamma square minus something times gamma and H minus 1. And I do not go back to the original form, but this coming from minus k by cube over 2, and this term comes from minus ky square times e. And now y is assumed to be Fano, so these are positive by Nakai's criterion. So these are every equations are positive. Then we look at this high school mathematics like graph. I mean, this is if we set this to be f gamma, then this is a quadratic function. So like this. Then this number, and then it is easy to show that we have this bound. So we have gamma somewhere, then at least it should be sandwiched by this bound, these lines. So this should be contained in this area. So gamma cannot go to here. Here it's outside this area. Then what we want is how to get when this value is larger than 11. So this can be over here. So okay, so we can show that this number -3. If we substitute x is equal to -3, then we get this bound because this is everything is positive, and this becomes 9 and -3, and this is 1. So this is at least 9 plus 3 plus 1 is 13, which is larger than 11. So we see that here -3 is of course negative, and but this is over 11. We have this symmetry axis, so this is s plus 3. So we further go to s plus 3, then this should go to over 11. This is above 11. And this value is 2 times s plus 3. So we get that gamma is less than 2s plus 3. Then after this observation, it is easy to get what we want. I mean, we can show that gamma is at most this one. So this strict inequality becomes strict inequality, and these are integers, so this becomes this. Then it is not so hard to get a bound for s. Then gamma is at most 3. Then we use the other equation C and use we give observation, but then we will achieve what we want. H is bounded. Okay. Let me just show you the important part. So we use this bound, and also this gamma becomes 3 by using this one. Okay, so this is a rough explanation on the proof of the case when rho and r are equal to 1. Before going to the next topic, I now want to summarize some differences between characteristic 0 and positive characteristic. First, as I mentioned, for this case, there are 2 open problems, and G can be equal to 11, and the existence of line. These are open in positive characteristic. Then, as for double cover, so if P is equal to 2, then it can be inseparable. So if you look at the classification table, it includes some double covers. So we have same classification table, but the double cover can be inseparable. The other difference is conic bundles, which again has a problem in characteristic 2. So from the next page, I will focus on this case, this conic bundle. So now skip this topic. Then the final one is a guide description. This is completely open. in positive characteristic. So Mukai's description gives explicit description for Fano threefold satisfying this property. So this means this condition is nothing but Picard number and index are equal to 1. For example, if G is equal to 8, Mukai proves that this is linear section of glass magnum 2, 6. And Mukai only give a sketch, but give a similar description for OG. And recently, Bayer, Kuznetsov-Macri gave a proof for this one. And anyway, so in character 0, this kind of description is known, but in positive characteristic, we do not know such description. We can get such a description or not. Okay. Anyway, so as I said, I want to focus on conic bundle. First, I want to start with the definition of conic bundle. We said that a morphism is conic bundle if both X and S are varieties and pi is a flat proper morphism and any fiber is conic. So this third condition is a fiber-wise condition, but it is not so hard to show that this is a globally. I think this conic vary continuously. So we have global P2 bundle and its fiber is inside this P2 bundle. So, and I give a general definition, but our interest is in the case when X is smooth Fano threefold and S is a smooth projective surface. And so if P is not equal to 2, then the picture is similar to or same as character 0. So if you are familiar with character 0 case, then only the new case is characteristic 2. There are mainly two problems. The first problem is this conic bundle for the Fano threefold from Fano threefold to smooth projective surface, and this conic bundle might be wild, which means that any fiber is singular. Let me show you one example, which is a famous example. We take P2 times P2, and the coordinate is X and S. Then we define X by this equation. So if we fix closure point, then the fiber is non-reduced because now A0 and A1 and A2 are an element of K, of the element of base field. So over the closed fields, this becomes like this. So any fiber is non-reduced. Any fiber is non-reduced. And it is easy to check that this is smooth and Fano. So this is a Fano threefold with wise conic bundle. But these such Fano threefolds are classified by Mori and Saito. So it is Picard number 2 and number 24 and Picard number 3 and number 10 in the classification table. So in what folds we ignore this wild case. So we consider the non-wild case. At least one fiber is smooth. So if one fiber is smooth, then general fiber is smooth. So we will consider the generically smooth conic bundle in what folds. So I said that there are two problems in characteristic 2. So one problem is a wide conic bundle. So the other problem happens even for the generically smooth conic bundle. Even if this conic bundle is generically smooth, the discriminant divisor can be worse than characteristic 0. For example, if the characteristic is not equal to 2, then this is a divisor on S, which is normal crossing and reduced. But if P is equal to 2, then the discriminant divisor can be very bad. For example, this can be non-reduced. So let me show you one concrete example. Again, we take P2 cross P2, and coordinate is X and S, and the base is P2S. The equation is like this. Then in this case, this discriminant divisor is S0 cube. So this is non-reduced. And also, if we take reduced structure, then this is a line.
Can you comment on this example? So what happens if I take a general line in P2, which is the base, and restrict your hypersurface to the preimage of this line?
Oh, sorry, you're asking what happens if we take a line and its inverse image?
Yeah.
So in that case, so it is actually, I think, quite different from the other characteristic. If we pick a line and its inverse image, then this inverse image is not smooth.
Yeah. So there's this again, this lack of Bertinia, right?
Yeah, this is a counter example of Bertini for base point free divisor.
And because I think that in dimension 2, there's no such thing as a wild. Okay, this is not wild anyway, but I think in dimension 2,
this is generally
should be
smooth,
smooth,
but
right?
still, I think this comes from the fact that this is non-reduced. For example, if this is actually reduced, then we can find a line such that its inverse image is smooth. So this non-reducedness is actually the key point in this observation.
And also for dimension in dimension 2, the discriminant is going to be always reduced, right?
Yeah. So I will now give a definition of this one, but this discriminant divisor commutes with base change, and this smoothness is basically almost the same as the non-reducedness of the fiber. So this is non-reduced, and the restriction to this one is non-reduced, then its fiber is non-reduced. It is isomorphic, it is equivalent.
Thank you.
Yeah.
I'm sorry, but can you explain again why the discriminant is given by S0 cube in this?
Okay, now I will give you a definition of the discriminant.
So it is not given by the determinant of the matrix? It's something different, is it?
It's slightly different, very close to that.
Okay.
So, very close to that, but slightly different. Okay, so now let me give you the example, definition of this discriminant. So this is a base almost given by these joint work. And I slightly, my contribution is almost epsilon, but anyway, definition is as follows. So this is defined, given a conic bundle, we can define discriminant divisor, which is a closed subscheme of S of the base, satisfying these two properties, which is maybe axiomatic. Okay. The first one is axiomatic property. So this discriminant scheme commutes with base change. I mean, if we take fiber square, then always we have this equality. The second one is local description. Given this situation, I mean, bases are fine, and X is globally embedded to projective P2 over this R, and assume that X is given by this
But you have
integrity equation.
two monomials xy here, so probably one of them is yz, right? So alpha xy and gamma xy.
Oh, sorry. Thank you.
Yeah.
Yeah. XY. Oh, X. Alpha should be. Sorry. Alpha should be alpha YZ. Sorry. Thank you. Yes. YZ, ZX, XY. Yes. Then discriminant is given by this. And this is answer to the question, because if we take symmetric, if characteristic is not equal to 2, we get symmetric matrix S. Then we take determinant. And after that, we divide this by 2. Then this is actually this one. So in very similar to determinant, but not equal. But not that this can be defined also in characteristic too.
Question about the first part. What do you mean by inverse image here? Is it pullback?
It's a scheme theoretic inverse image.
Okay.
So this is not the divisor. I said that this is closed subscheme. So closed subscheme and takes the inverse image scheme theoretically.
Yeah.
So these two conditions characterizes this closed subscheme, or usually divisor, and we have further good properties. So this is not the decision provided. This from here, maybe this is theorem, but anyway, we have the following results. So this locus parameterizes non-smooth fibers. So if conic bundle is generically smooth, then this delta is an effective quality divisor on the base. And this delta is equal to 0, is equivalent to the any fiber is smooth. Okay, so this is characterizing the smooth fibers in a sense. And also this delta knows where is non-reduced fiber. So assume that X and S are smooth, then singularity of delta is corresponding to the non-reduced fiber. So if the point of delta is smooth, then its fiber is reduced. I here say geometrically reduced because if S is closed point, then just reduced. But if S is a scheme theoretic point, then it is we should consider geometrical reducedness. But anyway, so it parameterizes. So this delta knows where is smooth fiber and where is reduced fiber. So I gave a Fano example, which is generically smooth. So I now want to give a local example. I mean, the S's are fine. So which illustrates how bad characteristic two cases can be. So so take S to be affine plane, and the coordinate is U and V, and we fix non-zero polynomial. And we take this equation, so which is contained in P2 times A2. Then this is this we can check that X is smooth, and this is a conic bundle. In this case, this delta is equal to gamma to the 4. So okay, so maybe we compare this one and this one and this one. So here only amongst alpha and beta and gamma, only alpha appear. So delta, beta, and gamma are 0 in this example. So this term is erased, and this term is erased, and this term is erased. And this 4 times something is 0 because the P is, we are now in characteristic 2. So delta is now equal to alpha times A times alpha square, and minus becomes plus in characteristic 2. Then we look at, so we need to compute alpha A times alpha square. So A is equal to 1, and alpha is phi square. So this is phi to the 4. So I now showed you the computation of this one. So in this example, X and S are smooth, but delta is phi to the 4, and phi is chosen to be arbitrary non-zero polynomial. So this means that when this delta pi, and even if we take its reduction, the singularity can be very, very bad. And also, this example satisfies the following property. If we to pick a close point, then the fiber of this one is not smooth. Then this is equivalent to the condition that this point is contained in that pi. And as I said, pi knows where is non-reduced fiber. It is characterized by singularity of delta. So this fiber is not reduced. Then it is equivalent to S is a singularity of delta. But now delta is singular everywhere. So these are equivalent. So this means that excess is generically smooth and every singular fiber is non-reduced. This is impossible in the other characteristic. In the other characteristic, usually it is delta is a normal crossing, so the picture is like this or like this. And singular fiber is non-reduced fiber is here. But in characteristic 2, delta can be, in this case, for example, 4 times x or like that. Then this is non-reduced everywhere. So every single fiber can be non-reduced. Then the final topic I want to explain this theorem, which which is used in the classification of Fano threefolds. So in Morimukai classification, they proved this equality. This plays crucial role in the classification of Fano threefolds. So my result is I extend this to positive characteristic case. And here, this is divisor times divisor. So this is codimension 2 cycle X. And dimension X minus 2 is equal to dimension S minus 1. So after taking push forward, this is a codimension 1 cycle. So it means it is nothing but divisor on S. Okay, so again, as before, we first start with the proof in characteristic 0. In characteristic 0, we first apply Bertini by taking general curve, which is intersection of general hyperplane section. Then C is a smooth curve, and its inverse image is smooth surface, which is conic bundle. So this is ruled surface. Then for the ruled surface, K square is basically the number of singular fiber. And if we take C in general, then it is corresponds to the number of intersection. So this is basically idea of the proof in characteristic 0. But as we mentioned before, so the Bertini fails in this situation. For example, if S is equal to P2 and delta is not reduced, so this actually appeared, this situation appeared for Fano conic bundle I mentioned before. In this case, actually, phi inverse C has a non-reduced fiber, which is a conic bundle, then this cannot be smoothed. So we need to consider alternative proof in positive characteristic. So we start with this universal conic bundle. This is a key case in the general case. So let me have a look how to settle this case. So universal means we consider the P2 over the base field, and this is parameterizing conic. Then this is P5. I mean, P5 has 6 elements, which corresponds to this coefficient. In this case, we can apply the strategy in characteristic 0 because singularity of delta is not so large. I mean, it is, for example, actually we can show that this is integral. So R1 is important. For example, if the base is 2-dimensional, then it has only finitely many singular points, then general curve can avoid this singularity. This general curve C avoids singularity of delta. This is an important part. So in this but example has big singularity. I mean, singularity is codimension 1 in the ambient space. Okay, so this is a proof for the typical case or universal conic bundle case. The general case is in a sense reduced to this case. We first with conic bundle given generally, then we pick a curve for normalization. Then we are reduced to the case when the similar to this one. I mean, similar means this is a relative version of this one. I mean, we consider this is a conic bundle associated to, oh, sorry, this is Y. So this is conic bundle. So we have P2 bundle, as I mentioned before. So this is relatively P2. So in our case, this is we consider absolute P2, P2 over K. But here, this is P2 over C. Then after this reduction, if we take a small affine open of C, then the singularity, the type of singularity can be computed from the absolute case. I mean, singularity is again not so large. I mean, this is R1. Then we can apply Bertini for this case. So now I want to stop here. Thank you very much.
Thank you.
Okay. Are there any questions?
Sure, sure.
But maybe while people are thinking about more advanced questions, I just want to ask a question about the last 2 pages. So you have proved some theorem about non-wild conic bundles, and but did you mean that then you apply it for to classify some Fano threefolds of Picard rank greater than 1? And so how does one apply it to the classification?
Also, how to apply?
How does one apply this conic bundle theorem to the classification of Fanos?
So if, for example, if we want to classify fancy threefold with Picard number 2, then we have, okay, this is text to S. If one extreme array is of type C, then if we pick D to the inverse image of line, also in this case, we can show that this is P2, and this is, we take inverse image of line. Then as before, we will compute this number. Then in order to compute, I don't know which one, but in order to compute this one, we will use the formula, this formula.
So, but by now you know the and then it gives you no, but I still I'm not getting this. So you know, okay, now you know that you are fibered over P2, and you know the discriminant, but does it really give you the description of the threefold? You know the base of the fibration, and you know the discriminant. For instance, how do you know where is it embedded? The conic bundle, I mean.
So, so if we look at the proof in character 0, so sometimes they use the assumption that the fact that this delta is normal crossing, but it's not so hard to avoid it in order to achieve the goal.
Okay, so I see. Then at least we have some additional information, which is always good. And maybe one more question. So just before the conic bundles, you mentioned that there is no Mukai description for Fano threefolds of Pk rank 1. And does it mean in particular that if we fixed some genus like G equal 10 or something, then we don't know that all such Fano threefolds are contained, say, in one deformation family? Do we know this?
So you mean at least one?
You mean irreducible, Kostya?
Yeah, maybe irreducible.
Otherwise,
yeah, sure, of course, irreducible.
So sorry, maybe I might not understand the question, but
no, I mean that if you have all these descriptions like Mukai description or maybe the description of, say, Fano threefolds of genus genus 4 as intersection of quadrics and cubics. They tell us that that all such Fanos are in one deformation family. There is some kind of parameter
irreducible,
family. Irreducible parameter family. Do we know something like this here?
The question is irreducibility of the moduli stack.
That would be moduli stack, yes.
I do not know because actually I wanted to prove the existence of a line. Then if we know the reducibility like that, then I think if we have a line for general member, then it should be enough. So I wanted to get such kind of results, but I have no idea how to achieve it.
And maybe another similar question. What people call Mukai description, I think it applies to Fano threefolds of with G starting from G equal to 6, right? Because up to G equal to 5, you don't need any Grassmannians to describe Fano threefolds in characteristic 0. They just completed the sections or like in weighted projective spaces, and up to genus 5. Do you have some explicit description in positive characteristic?
For genus, G is equal to 6 or?
No. Before excluding genus. 6, up to genus 5.
Up to genus 5, it's same as in characteristic 0. So
you can prove that, for instance, for genus equal to 4, they always quadrics and intersection of quadrics and cubics, for instance.
Yes.
I see. Thank you. Any other questions?
I have maybe a more specific question. To show that your Fano is intersection of quadrics, do you use Sandana results, right?
Yes, exactly, yes.
But as far as I remember, Sandana results are for characteristic not 2, for odd characteristic.
Oh,
How
really?
about? Yes. I think, as far as I remember, it like this.
Already. Maybe I might have overlooked it. I already. So sorry.
Yeah, this is written on the second line of the paper.
The on Petri's analysis of blah blah blah. The title of that.
Let me see. I don't. Maybe I have it. Ah, yes, yes. In the beginning, he assumed that characteristic is not 2.
Oh, sorry. So you're talking about the paper published from Masanare, 97?
Yes. No, no,
Sorry,
no.
73?
American Journal of Mathematics. This paper.
Oh, maybe I am talking about different. I am citing different paper. So I am using paper published in 73.
E3, yes.
So maybe it might be. So I'm talking about this paper.
Oh,
So I have did something stupid. This one?
not this one. American Journal of Mathematics. This is about curves.
What I am using is the result for curve.
I see.
As far as I checked,
I see.
but I did not follow the proof completely, so I might overlook something. But I thought that it was okay. But
So, do you have other questions or things to discuss? So if there are no more questions, maybe let's thank Hiromu again for such a extended talk.
You.